Now, we said that in 2 dimensions, these are related to tangent planes. Namely, if we have a function with 2 inputs and 1 output, we can draw a graph for that function. And it's going to be some kind of curved surface. And on that curved surface, we could pick a point and say, let's try and find the closest flat surface to that, closest tangent plane. There are a couple of ways to do that. Normally, when we're finding formulas for planes, like we've been doing before, we would take a point and we would find a normal vector and we would do a bunch of solutions for that. And that's fine. We'll have a slightly different method using this linear approximation with the partial derivatives, though. Here, there's a direct formula that says that the tangent plane is given by writing z, the output, as equal to the value of the function plus the x partial derivative times x minus a plus the y partial derivative times y minus b. So it's kind of like the formula for the linear approximation, except we have to do 2 separate contributions, one of them that goes along with the x slope, and one of them that goes along with the y slope. And this formula doesn't come from anywhere magic. It's just plugging in what the matrix of partial derivatives is going to look like in the specific case we're doing. So here on top, we have the formula for the graph of our function. And that's pretty close to this down here. This is the linear approximation. This is the closest possible linear function to the function we have. It's the value times the derivative matrix times the matrix of times the column vector of inputs times minus a b, the start point we're working with, and that's equal to f of a b plus the partial derivatives times x minus a, y minus b. And so if you expand it all out, that gives the formula that we were working with when we do the matrix multiplication. So the x partial derivative times x minus a plus the y partial derivative times y minus b. That's really all there is to it. It's just expanding out a little bit about the matrix of partial derivatives. So let's do an example. I had an example on the previous slide, and then I am too tired to correct it right now before I actually get it out. So let's write a function f of x, y is equal to xy squared. So that's the graph of the function if we set it equal to z. And let's find the tangent plane. At xy is equal to 3, 1, like so. So what we have to do is we have to say our tangent plane is given by the formula z is equal to f of 3, 1 plus del f del x evaluated at the position 3, 1 times x minus 3 plus del f del y at 3, 1 evaluated at y minus 1. And so we have to expand those out. We have to say, what's f of 3, 1? F of 3, 1 is 3 times 1, it's 3. The x derivative of this function, the x derivative of xy squared is just y squared. And if we evaluate y squared, well, let's write down the partial derivative. We want to evaluate that at the point 3, 1. And then the y derivative is going to be 2xy evaluated at 3, 1 times y minus 1. So here I'm just inserting an extra step to write down the partial derivatives. This gives me 3 plus y squared times x minus 3 plus 2xy is 6 times y minus 1. And so our total formula is going to be something like z is equal to x plus 6y plus 3 minus 6 minus 6, unless I've screwed something up, which is eminently possible. And if we want, we can move everything over to the other side and say that 0 is equal to x plus 6y minus 6.